Namaste and welcome back to JEE Physics with Typical Monk. This is class 38, Simple Harmonic Motion. A pendulum swinging, a mass bouncing on a spring, an atom trembling in a crystal, all share one hidden rule. Whenever the force pulling a body back to its resting place is proportional to how far it has strayed and always points home, the motion that results is simple harmonic motion. Its signature is F equals minus kx, and its acceleration, A equals minus omega squared x, is largest at the turning points and 0 at the center, exactly where the speed is greatest. Its displacement traces a perfect sine curve. Its energy sloshes endlessly between kinetic and potential, while the total, 1/2 kk squared, never changes. The period depends only on the system. 2 pi root m over k for a spring, 2 pi root l over g for a pendulum, never on the amplitude. Today, the law, the equations, energy, and the period. One idea at a time. Here is what you will master today. First, what simple harmonic motion is. Second, displacement, velocity, and acceleration. Third, the time period. Fourth, energy in simple harmonic motion. And fifth, the pendulum and the spring. One idea at a time. Let us set the foundation. Oscillation, a motion that repeats about an equilibrium. Simple harmonic motion, when the restoring force is proportional to the displacement. The rule: F equals minus kx, the force points back to the center. Mass line, acceleration is proportional to displacement and opposite in direction. Now look at the picture. Simple harmonic motion. The displacement, it traces a sine curve. X equals a sine omega t. The amplitude, A, the greatest displacement from the center. The time period, T, the time for one full oscillation. The restoring force, F equals minus kx, always back towards the center. Now, the equations. Displacement, x equals a sine omega t. Velocity maximum at the center and 0 at the extremes. Acceleration, r equals minus omega squared x, maximum at the extremes. Angular frequency, omega equals 2 pi over t. Now the period and the frequency. The time period, t time for one complete oscillation. The frequency, f equals 1 over t. A spring, t equals 2 pi, root of m over k. A pendulum, t equals 2 pi, root of l over g. Independent of amplitude, for small oscillations. Now look at the picture. Energy in simple harmonic motion. Potential energy, 1/2 kx squared, maximum at the extremes. Kinetic energy, maximum at the center. Total energy, 1/2 k a squared, constant throughout. The exchange, energy flows between kinetic and potential. Now, the energy of the oscillator. Potential energy, 1/2 kx squared, maximum at the extremes. Kinetic energy, maximum at the center. Total energy, 1/2 k a squared, constant throughout. The exchange, energy flows between kinetic and potential. The total energy is proportional to the amplitude squared. Now, the pendulum. The setup. A simple pendulum, a mass on a light string. The period, t equals 2 pi, root of l over g, only l and g. Small angles, simple harmonic motion holds only for small oscillations. Now match each formula to its meaning. F equals minus kx goes to simple harmonic motion. A equals minus omega squared x goes to the acceleration. 1/2 k squared goes to the total energy. And 2 pi root l over g goes to the pendulum's period. 4 pairs, each worth memorizing. Now, how many of these statements are correct? Statement 1. In simple harmonic motion, acceleration is proportional to displacement. Correct. Statement 2. The total energy depends on the amplitude. Correct. Statement 3. The pendulum's period depends on its mass. Wrong. It depends only on L and G. So the answer 2 are correct, statements 1 and 2. The trap is the pendulum in statement 3. Now, The two mistakes that quietly cost marks. The truth: in simple harmonic motion, A equals minus omega squared x, the acceleration opposes the displacement. The trap: thinking the pendulum's period depends on the bob's mass. The second truth: the total energy is half k a squared, constant, proportional to a squared. The second trap: forgetting that velocity is maximum at the center, not the extremes. Now test yourself. Answer in your head before the reveal. That is how G-speed is built. Here we go. Question 1. The defining law of simple harmonic motion. F equals minus kx. Question 2. The acceleration. A equals minus omega squared x. Question 3. The spring's period. 2 pi root of m over k. Question 4. The pendulum's period. 2 pi root of L over g. And question 5. The total energy, half k squared. Let us gather it all in one breath. Simple harmonic motion. The restoring force is proportional to the displacement, F equals minus kx. X equals a sine omega t, and A equals minus omega squared x. The spring, T equals 2 pi root m over k. The pendulum, 2 pi root m over g. Energy, potential, is half kx squared. The total is half ka squared. Now velocity is maximum at the center, acceleration at the extremes. Next class, waves. Order in the swing. Simple harmonic motion is nature's favorite rhythm. The pattern that appears the instant a restoring force grows in step with displacement and always points home. Namasia law is F equals minus kx. Its displacement is a clean sine wave. Its acceleration, minus omega squared x, is fiercest at the turning points and vanishes at the center, exactly where the speed peaks. Energy is never lost, only traded, all potential at the extremes, all kinetic at the middle, and their sum, 1/2 k a squared, forever fixed by the amplitude alone. And the period keeps its own counsel, 2 pi root m over k for a spring, 2 pi root m over g for a pendulum, deaf to how wide the swing. Learn the law, the equations, the energy, and the two periods, and every oscillation in physics becomes familiar. Next class, waves. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time, you will crack G. I will see you in the next class.